Thank you, Jakob and Omar, for actually really a nice workshop with many fascinating papers. So the paper today is joined with Tibor Heumann and Stephen Morris. It's entitled Selling Impressions, Efficiency versus Competition. And we want to talk about impressions in the sense of digital advertising and their relationship to online ad auctions. So as you know, web content is primarily monetized by ads, and the opportunities to show ad either in search or in display advertising that are provided to you by browsing a website is what it's referred to as impressions. And these impressions are monetized by the seller, who we want to think about as the publisher of the website that the user is visiting, and the bidders are bidding basically for the eyeball or the intention of the viewer, and that means that the object of the auction is the viewer. So think about an example: the publisher is the New York Times. A viewer is opening the front page of the New York Times virtually. A possible bidder for the eyeball of the user is Bank of America. In digital advertising, private information takes a particular distributed form that we're going to try to explore and investigate. And we want to think about this basically as a model of two-sided private information, namely, the viewer, who's the object of the auction, has many attributes: demographics, past browsing behavior, past purchase, income, and so on. And so these are the attributes. That's one side of private information. When we want to think about the publisher as basically having some possession about the nature of those attributes of the viewers. The advertiser, by contrast, they have private information about their preferences or their willingness to pay for specific attributes of the viewer. And the value that is being created by the match between advertiser and viewer, or the impression, is jointly determined by these different sources of private information. Attributes on the one hand side, preference on the other. The question that we want to ask and answer completely here is, what's the optimal information for the seller to reveal about the quality of the match in order to maximize the revenue? And we're going to ask this question in the context of a standard second price auction that is the basic model that is used in a lot of internet advertising. The subtitle, Efficiency versus Competition, or Efficiency versus Market Sickness, is meant to signal the trade-off that we want to model. Namely, by providing more information about the attributes, we improve the quality of the match and hence the social surplus that we can realize. But we also creating lesser competition and thus higher information rents for the bidders. And so one might ask whether it's optimal to either fully reveal all of the information or not reveal. And the answer, the complete answer that we're going to give, that is in fact optimal to fully reveal the quality of the lower matches, so have full revelation when competition will be high, and to pool in one big pool the value of the premium matches where competition will be low. In fact, the threshold where we will start pooling is going to be determined by a critical quantile of the distribution, and that quantile will depend just on the number of buyers, but will be independent of the distribution of the value. So it will not depend on the distribution of values, whether it's uniform, normal, or whatever you would like to take. Okay. Okay, so I think what we want to think about this here is what the heterogeneity on the two sides of the market does do, and to what extent we want to allow and to what extent we want to suppress heterogeneity in order to introduce more competition. The interpretation of the model today is going to be very much tailored towards digital advertising, but many of the issues appear in other areas. For example, when we want to sell an asset that bundles or unbundles financial claims, we are also driven by similar consideration. And so I want you to think of this as part of a larger class of problems. Okay. This paper will make two contributions. The first one will be the characterization of the optimal information structure. The second one will think about how to implement the revelation of information in an incentive compatible manner in the auction. And so here we will think of broadly two classes of revelation mechanisms that we are associated with the names of automated bidding and manual bidding. These are terms that we borrow from the computer science literature and from the literature of digital advertising. In automated bidding, essentially the bidder will reveal some information about his preferences, and then that information will be fed into an algorithm that bids on behalf of the bidder. So at the first instance, we only have truth telling as a constraint. In manual bidding, we actually have a second set of constraints, namely after the initial revelation of information about attributes, the bidder then receives a bid recommendation and can then choose to adopt or not adopt this impression at this bid recommendation. So in that sense, we have a second set of constraints, often referred to as obedience constraints, and that will make, of course, the problem of designing the optimal algorithm much harder. We'll have very positive results, in general positive results on auto bidding, and those I will focus on today. We have more limited approximation results for manual bidding, and given the half hour that we have, I think I'll focus on auto bidding today. Okay, so this is just a little copy on the lower end of the screen of the characteristics that the bidder can enter, say, on Google Ads when they want to choose how they want to bid on particular characteristics of the viewer, so device, location, the time, the content, the targeting method, and so on. Okay, just to give you an idea that these are elements that are used. Increasingly, of course, we will see a move from manual bidding to automated bidding, because the problem is essentially how to condense this high-dimensional information into immediate, instantaneous bids on the websites with minimal latency, so that everything can be created instantaneously. Okay, so I'll give you the model. I will spend a little bit of time on that, though. I'll then present you the main result. I will have some results for large markets, as we think of those as the conditions prevailing in the internet, namely at least a large number of potential bidders being interested for any particular viewer. And then I will have some results on algorithmic bidding and implementation of the information structure. Yes, and of course, feel free to interrupt me. Now is a good moment, or after I present you the model is another good moment. Okay, so let me give you the model. It is going to be a bit more specific than for the results as we derive them in paper, but I thought the concreteness might help you to think about this. So we want to think about n advertisers who bid for a viewer in a second price auction. Each viewer has a number of binary attributes that can be either -1 or +1, and each advertiser has preferences for these attributes, -1 or +1. And the value of the match is being created. The value of the impression is basically being created by the match between the attributes and the preferences. So whenever the sign agree, we get a positive increment to the match value. Whenever they disagree, we get a negative sign or negative increment to the match value. I'm just normalizing by the square root of the number of impressions, because in much of the model, we'll be interested in focusing on the case when there's a large number of attributes. So we're going to take the limit. And in this case, this will generate naturally the standard normal distribution. Yeah. Sergio, you are unmuted. I'll see you talking, but perhaps not to me. So
no, I just said to myself, and you get a normal distribution, as you were saying. That was nothing.
Great, good. Okay, so the match value is basically just being created by the match of attributes and preferences. And the value is then simply an increasing function of this scalar, which identifies the value of the match. And you can easily see that even if we have symmetric distribution about attributes and characteristics, together with the valuation function, which is simply assumed to be monotone, we basically can generate independent values among the bidders with any arbitrary distribution. So it's a pretty permissive model to think about the value distribution of the advertisers. Okay. Just to give a full description, I anticipated this already. We're going to think about this as independent and uniformly distributed. Together, they basically induce, just as I mentioned before, through the value function, a true underlying distribution of values. And that's the distribution that we will work with in the first part of the talk, and then we will return back to the underlying model, the generating model, as you wish, about attributes and characteristics. The one point I should perhaps emphasize here, the way we thought about the independence and symmetry between attribute and preferences basically make it such that the attributes generate horizontal differentiation among the bidders that is independent across the bidders. So what this model is generating is a model of independent private values of the bidders. That's the substantive restriction of the current model. We love, of course, to think about elements of correlation, but we're not quite there yet. So this is what we're starting with. Okay, and just as Sergio has anticipated, in the case that we had many attributes, this is just going to move to the standard normal distribution, and then feeding it through the valuation function generates a distribution of values that is quite flexible in terms of what this distribution is looking like. Okay. I apologize if I'm going a little bit fast, but I hope that's okay. Good. The first question, the information design, is the question we're going to map. We're going to provide a signal as a function of the elicited attributes and the elicited preferences that informs the bidder about the posterior expectation he should have over the value that is being offered to him. Okay, so the bidder knows his own preferences. That's why he will also get from the seller a signal that allows him to further refine his estimate about the underlying value, and we're going to call that the WI. And so the question of the information design is basically, how do we want to choose the signal structure such as to influence the posterior expectation of the bidder, and with that, the distribution of bids by the bidders. Okay. In automated bidding, we're going to just think about truth telling, and then going to implement in the second price auction the bidder optimal bid by namely pricing exactly equal to the expected value. Okay, so we're going to have just one set of incentive constraints. In manual bidding, we have, as I mentioned before, truth telling and obedience, but let me not dwell on this further since we won't have time to develop the ideas here much. Okay. The objective that we're pursuing is, from the seller's point of view, to maximize the revenue in a second price auction. Today, he has not access to any tools other than the information policy. So there's no participation fee, there's no reserve price, although that can all be integrated. All he has is to shape basically the distribution of the posterior expectation to increase the revenue that is arising in the second price auction. So what you would like to do, in essence, is what I have in this last equation here, is to choose the information structure in a way as to maximize the revenue that is going to be simply the second order statistic of the posterior expectation of the bidders. Yes? So the richness of the preferences and attributes in terms of independence and symmetry will allow us to essentially choose any information structure so that we are unconstrained with respect to the shape of the distribution function, except for, of course, the base plausibility or base consistency. Okay. What we are after here is a little bit the notion of conflation that was first suggested by Levin and Milgram as a way to think about digital advertising, namely to choose in some sense the narrowness and the broadness of the object that we're going to sell, and we're going to show in some sense that there is an optimal way to choose to conflate goods and to be similar goods in order to influence the revenue. Okay. There's some recent very nice work in computer science to think about automated versus manual bidding, and so we're borrowing their language. This language this work focuses mostly on indirect mechanisms such as first price auction and much less on information. So in that sense, we bring this language to the question of information. Great. Let me state you the first result and give you sort of an idea how we're going about it, and then present the two additional results on large markets and then on automated bidding algorithms.
Dirk, sorry to interrupt. Related to the related literature, there's a paper by Tenenholz et al., which I think is even more strongly related.
You mean the paper by Pines Lemmer?
Yes.
Yes. Okay. Good. Yes, absolutely. And we cite it in our in the paper. So, but thank you for reminding me. I should mention that here. Yep. Wonderful. Good. So here we are. We basically now have realized that what we need to do is to shape the distribution of the posterior expectation. The distribution of the posterior expectation in particular, we want to shape the second order statistic, and that's that is the second line here, right? And what we're trying to do is to maximize this expectation. Okay. The two problems that we are facing is that, or perhaps I should just dwell on this, is that of course we need to find a good description of what are the set of feasible distribution relatively to the given distribution F. And then in terms of the optimization that we face here, we see that this is an optimization problem that is highly nonlinear in the variable of interest, which is G. It's neither convex nor concave. It's certainly not linear. It's neither convex nor concave. So at first, we can make little progress here. Okay. The feasibility is actually more standard because we basically know that we can choose any distribution G as long as F is a, I have a very sensitive mouse, as F is, as long as F is a mean preserving spread of G. Right? Because of course, F, the true valuation distribution, must be mean preserving spread of our posterior expectation, because the posterior expectation at most can tell us as much as the true values are and possibly can tell us less. Okay. So that's our maximization problem that seems a little bit hard or difficult to access. And what we're going to do in the first step is to basically rewrite it so that we're going to be able to formulate it as a linear program, and we still have a nice description of the set of feasible distribution. Okay. And the way that we're going to do is to basically rewrite it not in terms of a distribution of values, but in terms of a distribution over quantiles. Okay, so of course, we're not interested in the quantile of the individual values. We're interested in the quantile of the second order distribution. Okay. But just as the quantile distribution of any random variable is uniform independent of the underlying distribution, so is a distribution function of the quantile of the second highest valuation independent of the underlying distribution and just dependent on the number of bidders or the numbers of samples that we draw to get to the second highest distribution. Okay, so we essentially have a distribution function that is not quite as nice as a uniform, but it is constant across all distributions, if you wish. Okay. And so indeed, we can rewrite the revenue problem by using the quantiles and using the measure of the distribution of the second order statistic, okay? And then using the inverse function, using that quantile as the object that we want to maximize. So now we have a linear program, and we have a new constraint, namely that we're not ordering f and g, but the inverse, the quantile of f and g. But there's a nice result in the literature on stochastic orders that order is in fact just the mirror, that is the order of the quantiles, in fact just mirrors the order in terms of mean preserving spread of the underlying distribution. So this is a well-defined optimization problem. Okay. And in fact, it's linear, and some recent work on extreme points of such optimization problems by Philip and Ian Benny is what we're going to appeal in order to verify the optimality of our solution. Okay. So our claim is that the optimal distribution, the optimal information structure, the optimal symmetric information structure, that's the one caveat that I should mention, is simply given by a signal that is completely revealing as long as we are in a quantile below a critical threshold Q star, and it's completely bundling, that is, it's telling the bidders only that their value is such that it exceeds a certain quantile threshold Q star otherwise. Okay, and that Q star is independent of the underlying distribution of values and just depends on the number of bidders. So it's really the sampling and the level of competition that matters, not so much how the exact distribution of values in the population looks like. Okay, so it's a very simple information structure that is allowing for complete ranking and noiseless information on the lower end and complete pooling on the upper end. Okay, and that's it. Okay. So if I'm translating this into the bidding behavior in the second price auction, it basically means that we're going to create competition at the top of the distribution, because if it so happened, first of all, we compress the values. And of course, by creating an atom in the top of the distribution, we make it more likely that in fact the second highest value is equal to the first highest value, and that therefore the bidder at the highest bidder doesn't get any information right. Okay. That comes at the expense of limiting the efficiency of the allocation at the top. It turns out that the seller is willing to incur that loss of efficiency in order for a depression of the information end. As we know, the information end in these quasi-linear models is typically going to be convex for the bidders, and so by using that pooling at the top, the creating of the inefficiency in the top, which is again in contrast to sort of our intuition in standard adverse selection, we're going to create more competition, even though we're giving up a little bit on efficiency.
5 minutes.
Great, thank you. So that's the first result. It's a result that we can very nicely translate in terms of the characteristics, because we basically the literal translation of this information structure is to say we can tell every bidder the number of matched features or matched attributes up to threshold level n star. Above that, we're simply going to say you have more than n star matched attributes, but I won't tell you more. Okay. With 5 minutes, I won't have time to go through the geometry, but it's basically the reverse geometry of convexification. We're going to do a convexification simply because we switched from distribution to quantiles, but the logic is the same. And then of course we have to return back from the quantiles to the distribution. So you can see that in the slides. The quantile is determined as a solution to this polynomial. The one thing I want to take with you from here is that quantile is increasing in n. So as we have more and more competition, we can give up on bundling because competition will already depress the information rent. And a different statistic that we just found out yesterday that I haven't time to display here is what's the probability that both the winner and the second highest bid are in the pool. And the interesting result here is that probability is going to converge from below towards 0.53. So it's part of a Poisson distribution, which means that bundling is going to stay relevant even with large amounts of competitors, because we're going to still be able to depress information rent by allowing for competition. Okay, so the impact of the information on the revenue is going to be remaining even with large number of bidders. And so to verify that the given conjecture or the geometric argument is indeed constituting the optimal information structure, we can use this verification result in a recently forthcoming paper, I think in Econometrica, by Andy, Philip, and Benny. All right. Good. If I have just 5 minutes, then let me not talk about large markets, those paper you can see in the paper. Let me rather talk about the algorithmic bidding. Oops. Oh, I went in 2 steps here. Okay, let me just. Okay, so now we basically pretend in the first part of the talk that we have complete freedom to modify the distribution of the values of the bidders subject only to the mean preserving spread constraint. Now we want to show that if the information structure that we have derived in the first part is the one that the auctioneer is going to try to implement, then the the bidders have an incentives to nonetheless reveal their information truthfully to the seller. Okay. So the revelation game that we are playing here, or that we are designing here, is that we say each bidder can declare their preferences, okay, in terms of this large vector of preference vector. And with that, I'm then going to compute as a seller the bidder optimal bid in terms of the expected conditional value if I'm using the information structure that we have just derived. And the result that we want to establish in the end is that under auto bidding, and given the optimal information structure towards we're heading, it is a dominant strategy for the advisor, for the advertiser to report his preference truthfully. So this result here is targeting immediately the optimal information structure. Is not a result that gives us a complete description of what is the set of feasible mechanism in this high dimensional preference space, but it tells us that if we look first at essentially a relaxed problem for the seller, and now thinking about whether that relaxed problem satisfies the standard truth-telling condition, then the answer of this proposition is that indeed they can be satisfied. And the idea is that the truth-telling essentially maximally correlates the bid and the value of the advertiser relative to any other misreport. And in fact, the second best report that the advertiser could choose is to simply reverse all of his reports, namely whenever it's a plus, report a minus, and conversely. So there's sort of a bang-bang structure in the nature of the incentives. If I want to deviate, then I want to deviate maximally. And then in a second step, we show that, in fact, that's dominated in the optimal information structure, and of course, related problems by reporting truthfully. Okay. And I think with that, let me just flash that if we had manual bidding, then this optimal information structure would not be both truth-telling and obedient, but by creating symmetry in the pooling between the top and the bottom, we would reestablish both truth-telling and obedience, and we would get, in terms of revenue, something that approximates the optimal mechanism very well when we have a large number of bidders. So there are positive results to be reported for manual bidding as well, but we will rely then on an approximation argument rather than on exact optimality. Okay, and I guess with that I'm ending. Yep.
Thank you. Thank you, Dirk. We have time for one quick question.
I have a question. in fact, it's completely orthogonal to your talk, and it's probably the wrong crowd to ask this question. But nevertheless, I don't know anything. Is there any empirical data on whether people are misreporting more under automated bidding than under actual bidding? I mean, under automated kind of mechanism versus. Anybody knows anything empirical about that?
It's a concern for basically all the digital platforms. So a lot of the design by people who ran the algorithm at Google, at Facebook, but also at third-party auction platforms is very much concerned with that issue, and gaming by the advertisers. But I don't think we have much public data about that.
I see. Yeah, I suspected so.
Yes, but they yeah. So I guess friends in the industry told me that's sort of a main concern for them, and a lot of the tweaking of the mechanism is related to the fact of eliminating in some sense gaming or a misrepresentation on crucial segments or crucial preferences.
I want to jump in with maybe an observation / question. So apparently you don't get efficiency. I mean, there's this tension between market thickness and efficiency. And so an interesting observation that comes out of it is that what happens if you have competing publishers? If you have competing publishers, then as the result, each publisher faces a thinner market. And surprisingly, you can get even less social welfare when there's competition. So in contrast, say with my talk, when there were more senders, there was more information to the receiver. Now, the intuition suggests that with more publishers than one, it could be the case that markets become thinner, and therefore each publisher actually divulges less information than he would have as a monopolist, which I think is kind of a surprising observation.
Yes, that sounds right. I'll think about that a little bit. Yeah.
Yeah, so I mentioned, yeah, okay, I'll send you something also.
Yeah, absolutely. Thank you. Very nice seeing you.